Alright. Alright, Chapter 13, Thermodynamics, Hamid Magachi, SCID, Ferzan Persini Jad, PhD, Introduction. Thermodynamics is the study of the property domain with particular in relations among properties, change of the value of either of the occur spontaneously resulting from interactions with other objects. Ultimate goal of thermodynamics to understand the operation of thermal systems, able to design these systems and recognize opportunities to improve the performance of existing systems. Presentation is divided into 5 major categories: definition, term, vocabulary, thermodynamics, developed in the provided framework, explanation of thermodynamic principles. Laws and principles. Laws and principles described in relationships among properties of the matters are presented. Material systems are systems of materials that can form in the context of thermodynamic systems are introduced. Certain special cases, general expressions, some of the basic laws, principles are simplified, and some new relationships are introduced. Application of basic principles apply to systems frequently encountered. Specific methods analyzing these systems are presented. Heat transfer, 3 modes of heat transfer are presented. So we have definition, definition, terms, laws, principles, material systems, applications, heat transfer, and summary. Alright, 13.1. Definition of the term system is defined with a description of the material contained with the boundaries that contain in it. The 2 main classifications of systems are open system material may enter into, exist, and from the system may source call this type of the system control volume. Closed system material may not enter into, exist, and from the system may call the source call this the type of the system as a control mass. A property is a property attributed to the system with which value can be assigned with a describe the system and necessary for the feature of the property. The value can be stated with a given time and independently of the value within another time and independently of the process by the system arrived at its state. Intensive properties are independent of the mass of the system. Example, the temperature of the pressure. Extensive pressure properties are proportional to the mass of the system. Example, of its volume. Specific properties are determined by the dividing value of the extensive property by the mass of the system. Scientific property specifically property frequently denoted lowercase version in a letter sheet that represents the extent of the property. For example, volume of the system is equal to the volume of the mass of the system, specific volume of the system. State of the system is conditioned at an instant time to determine the value of the set of the independent properties for a system composed of a single macroscopically homogeneous substance of the equilibrium state with the special of the values of any 2 of the independent properties. Values of all other properties can be determined from these states. Interaction change of the system may either take place spontaneously without a corresponding change of the environment or occur through interaction with the environment. All interactions take place through the boundaries of the system. Typical interaction studies here are working interactions, heat interaction, bulk flow interactions, processes. A description of the evolution system from one state to another. Some special types of processes are reversible process where there exists another process of the return system of the original state, leaving no effect on the system's environment. A true reversible process can be achieved in practice, and all real processes will experience loss transfer energy that can be recovered without changing the state of the environment. The utility investigates reversible processes that provided a limited to the change in state that can occur in any process. Irreversible process which does not exist in another process that can return the system to the original state without changing the state of the environment. Real processes are irreversible, adiabatic process that all transfer the energy occurring with the work will occur through work interactions. Constant property process during which the value of the one property remains constant while such of the process occur. The analysis of the process usually simplified isometric constant volume process, energy transfer, closed rigid container, isothermal, constant temperature process, condensation evaporation, heat exchanger, isobaric, constant pressure process, weighted piston cylinder, isotropic entropy process, ideal turbine, isothalpic, constant enthalpy process, flow through a valve. Alright, 13.2, Laws and Principles. A few general ideas comprise the science of thermodynamics. 2 of these ideas, the first and second laws of thermodynamics, introduced along with the concept of the balance of the equation. In this section, mass balance equation thermodynamics system can be frequently analyzed solely for the accounting of all the possible change of the value of the additive material, the general of the time of the rate of change of the value of the additive property with equal to the algebraic sum of the rate of which an amount of the property can cross the system boundary and rate of which amount properties is produced and destroyed. For example, in this case, the additive property mass of the balance equation. additive mass over the additive time equals mass transferred plus mass produced or destroyed. M transferred is algebraic sum of the mass flow rates of all material systems into and out of system. Given the sign convention of the mass flow rate is positive the flow of the material into the system and the negative into the flow of the material out of the system. By definition, mass transferred is for a closed system is zero. For nuclear reactions can be neglected, mass is neither produced nor destroyed. In terms of the equation, mass produced or destroyed is equal to zero. Energy and energy balance of the equation. Mechanic concept of energy is well defined. The kinetic energy relative to the motion of the rigid body with your potential energy relative to the position of rigid body with gravity field of the thermodynamics concept of the energy a little more complicated. Each individual molecule of the substance that makes up the system can possess finite amount of energy stored in a number of different modes. For example, each molecule can have the kinetic energy due to the translation motion, kinetic energy due to the rotational motion, and a potential energy vibration of the molecule atoms with respect to each other. Total energy for the substance summation of all the type of the energy of each of the molecule that makes up the substance. Because of the number of the energy modes associated with each molecule, there can be larger number of the molecules associated with the real system. The extremely large is not possible to perform summation directly. From a macroscopic system, the easiest types of the energy to consider separately with the kinetic and potential energy of the energies associated with all the other modes energy stored are grouped together in the property named internal energy denoted with a capital U. The internal energy of the substance relative to the total energy by the following: energy of the total energy of the substance of the internal energy of the substance times the mass of the system times the velocity of the material in system squared over 2 times the mass of the system times the acceleration of the gravity times the height of the gravity field. Where E is specific energy of the system, bulk BTUs, and over pounds of matter, meter, and U is specific initial internal energy of the system. The balance equation of the energy contains the essence of the principle known as the first law of thermodynamics. Is given the energy is over the energy time is equal to the energy transferred plus the energy produced or destroyed. Energy is commonly transferred through work of the W heat and Q bulk flow interactions. At 3 types of transfers are possible. The open system bulk flow is not allowed in a closed system. Work interaction, or W, energy transferred due to the mechanical interaction between the system and the surroundings. The value of the work is considered positive. System where the performs work on the surroundings. Energy is removed from the system. The type of the work commonly encountered are shaft work, boundary work, and flow work, given in the following equations. Energy of the energy of the total work is equal to the negative work. Shaft work is equal to work started work system times the time total work. Boundary work is work time the boundary plus the parameter times the voltage over the voltage time, and the pressure of the pressure times the volume of the system over the distance and the time. Flow work the rate of which energy is work from energy frequency is equal to the mass of the flow entering the system times the pressure in the system times the volume of the system. Pressure volume diagram, figure 13.1 can be used to graphically compute the boundary work done on or by closed system during a reversible process shown. Work by reversible is equal to the derivative of 1 and 2 of the pressure of the differential in the volume. Work based on volume is equal to the derivative of 2 over the pressure times the direction of the volume. Work done on open system during reversible process. Work reversible is equal to negative 2, the derivative of negative 2 to 1 over the voltage drop and pressure. Heat interaction. Heat interaction is the transfer energy that occurs when 2 system differential temperatures are placed in contact with each other. In all cases, the transfer of the energy from high temperature system to the low temperature system, we choose to use the sign convention of the energy transfer heating interaction is positive if the energy is entering the system. Q is the rate of energy transfer of the heat interaction, bulk flow interaction. For each material stream that enters system, the two values of the energy transfer occur with the energy of the material that enters the system is added to the system. Material performs flow work on the system. Total energy is transferred to the bulk interaction is given by total energy bulk fission is equal to the mass times the well, where we go from U? Internal energy over the volume squared over the 2 times G times Z, or plus P, the mass times the P times the volume. Enthalpy is H times the internal energy times the pressure in the system times the volume. Where these are multiple inlet outlet streams, each of the stream contribute to the transfer energy. In this case, the total energy transferred. Because of the ball flow and the sum of the amounts of energy transferred in all fluid systems is where subscript I indicates flow in the system, subscript E indicates flow of the system out of the system. Again, nuclear reactions are negligible. Energy produced or destroyed is equal to 0. Note that the nuclear reactions cannot be neglected. Energy can be produced, but only can come in some mass. Conversely, energy can be destroyed, but only if there's a net gain in mass. Nuclear reactions are considered there must be conservation of mass and energy together. In other words, the balance equation mass and energy may be only considered together. The term for mass produced destroyed may be related to terms of energy power produced and destroyed. All interactions combined with the first law of thermodynamics, the balance of the equation, all types of interaction may be combined to produce an overall balance equation for energy. Distant energy over the time times the quantity times the weight times quantity times the work times the logarithm of the mass times the heat interaction times voltage squared, velocity squared over 2 times grams times Z. Relationship is known as the first law of thermodynamics is valid, but the nuclear reactions are negligible. Liquid water is very high. Specific heat, its temperature does not change much. Alright, cyclic machine. Cyclic machine is a device collecting with a device that allows continuous exchange of energy between systems. Will often change energy from one form to another. The machine must operate on a thermodynamic cycle, that is, a series of processes in which the ending state of the last process is equivalent to the beginning of the state of the first. System A and System B, figure 3.2, the after-thermal reservoir with the idealized system that will receive the amount of the energy through the reversible heat interactions, yet these temperatures will remain the same. Common example of the thermal reservoir in the ocean. Although there are many machines in the utilize heat interactions in the ocean, water-cooled boat engine, power generator plant, overall temperature of the ocean remains unchanged by interaction with these machines. Second law of thermodynamics have been misstatements of the second law of thermodynamics. All of the description and observation of all of the type of the real thermodynamic systems have never been violated. These observations are: the first, transfer energy occurs only with a preferred direction, namely high temperature, low temperature heat interaction, high pressure, low pressure, and boundary work interaction. 2, there's no real process 100% efficient. These statements are second law of the modified to agree with the language of the discussion are given below. Classiest statement: impossible to devise a cyclic machine that produces only and effectively transfer energy through the heat interaction low temperature body to a higher temperature body. Calvinic Planck statement: is impossible to devise a cycle machine that will have no other effect than extract energy from the reservoir of the heat interaction to produce an equal amount of energy through the work interaction. Sperata statement: almost all the possible states of the system with a given value of energy will give the states of values of the amounts of the constitute with the parameters. Therefore, the excite only one in one equilibrium state. Moreover, starting with the state of a system, it is possible that each equilibrium state with the arbitrary specified state value of the amount of the constitute with the parameter definition constitutes or substance that make up the system. Parameters or volume and any other system property that describe external forces placed on the system. Availability. Availability is called the energy or available symbol. Available energy. Theoretically, maximum amount of energy can be extracted from the system in the form of the useful work. Availability of the system cannot be specified by itself, but must be specified by the reference of the environment large enough for the interaction. If the system does not measurably change the state of the environment, the concept of the cyclic machine describes earlier can serve as to help demonstrate the concept of availability. Assuming the thermodynamic system connected with the environmental with a reversible ideal cyclic machine shown in figure 13.3. Okay, the concept of the cycle machine discussed earlier and can serve to help demonstrate the concept of availability. Assuming the thermodynamic system with the connected with the environmental with a reversible ideal cyclic machine shown in figure 13.3. For purpose of the description, assume that the temperature of the system is greater than the temperature of the environment, that the system and the environment interact with a cyclic machine. Heat interaction, cyclic machine begins to operate, energy is transferred. thermodynamic and into the environment, and additional energy is transferred from cyclic machine V with the work interaction because the system at its finite extent with the temperature will begin to drop. The energy is removed. Cyclic machine will continue to operate until the temperature of the system equal to the temperature of the environment. The total amount of energy transferred through the work interaction from time of the cycle the machine begins to operate until the stop of the equal of the system availability energy and initial state because the energy is transferred from the cyclic machine both through the work interaction, heat interaction into the environment. Clear availability of system A is less than the amount of the energy transferred from the system state of system, of which value of the availability is zero. System state of the cyclic machine stop operating. A state is known as the dead state in the system. Of course, the values of the certain key properties of the system, pressure and temperatures, are equal to those of the environment. Balance of the equation of the ability is also known as the availability of energy over the distance of the total, and the total amount of energy is transferred equal to the destroyed and available to transferred and destroyed. Entropy and entropy balance of the equation. Entropy is related with the difference between the amount of the system energy with the amount of system availability. The amount of energy that can be used to produce the work. The definition can be represented as follows. Where T is absolute temperature of the environment, subscript it refers to indicates value of the arbitrary reference state of the system. The balance equation is entropy entropy over the time, and the entropy transferred plus entropy produced often refers to entropy generated or instead of entropy produced. These terms are related to a reversible process. Balance with entropy for all these types of interactions considered work, heat, and bulk flow. Total rate of entropy through the heat interaction, total rate of entropy through bulk flow interactions. In equation 1319, temperature of the system boundary at the point of the heat interaction. A curve of the temperature may or may not be constant with respect to time of the position of the system boundary with no transfer entropy and work interaction. Entropy produced in term is related to the irreversible that occurs in any real process, Clausius inequality. Historical statement that closely related to the second law of thermodynamics can be derived from the entropy balance equation, closed system operation in a cycle. Statement is known as the Clausius inequality, given as the Alright, the increase of entropy will also reduce work output. Temperature entropy TS diagram. Temperature entropy TS diagram. Figure 1315 can be used to complete graphical energy transfer reversible heat interaction as shown below. Reversible temperature entropy. Our availability balance equation. The balance equation is availability of the availability equals transferred minus destroyed. Availability is never produced or reversible. The system destroys availability by the same process to determine the balance equation with the other additive properties discussed. The balance equation and availability can be derived with this equation, where the flow rate is availability amount of the availability transferred during the bulk flow, where the interaction is given, and the flow availability is the maximum amount of energy the flowing material can transfer through the work interaction. Properties. We now switch our full focus to the definition, basic law of the thermodynamic description, substance for the makeup of the thermodynamic system. First type of simple substance we consider is a simple substance with a different type of the substance for the ideal gas discussed in section 13.3. We define simple substance for the substance with the microscopically homogeneous, isotropic homogeneous, meaning that there are no way to distinguish material in any location system from the material in any other location. Isotropic meaning that there is no preferred spatial direction in which any interaction will behave differently than if applied from any other spatial direction. Definition can be applied with a single substance such as water as to homogeneous mixture substances such as air, which is the mixture of oxygen, nitrogen, and other gases. Enthalpy. Often in certain types of systems are investigated, a group of the properties will arise naturally. On such properties, enthalpy will appear naturally with the bulk flow interactions are considered by analyzing the entropy balance equation of bulk flow interactions. We find energy transferred related with the change of the value of the following property equation as U times P times V. Group of the properties can be frequently, even though they have given its own name. Enthalpy has been traditionally used property directly in analyzed thermodynamics. The expression enthalpy is H equals U plus PV. In terms of specific property, H plus U plus VV. Enthalpy has units in BTU or kilojoules. Specifically, enthalpy has units of energy per unit mass, both in BTUs over the mass. The Gibbs-Hertz Helmholtz free energy, just an idea that anticipating the naturally arise with the analyzing bulk flow interactions. Two other properties that naturally appear with the thermodynamics chemistry reactions are examined. Gibbs free energy to define an equation 1327 appear with a chemical reaction at constant pressure for the temperature examined. In terms of specific properties, Helmholtz frequency energy defined as the equation appears with the chemical reaction occurs at a constant value with the temperature as A to the U times Ts. The term specific properties A, U, Ts. Both Gibbs free energy, Helmholtz free energy have unit energies of BTU kilojoules and mass specific form of the units of energy per unit mass. Alright, specific key for the current experimental techniques of the device thermodynamic property, the easiest of the measure of pressure, volume, temperature for the given the equilibrium state with the system comprised fixed amount simple substance with the determinate value of the two independent properties to be no internal energy of the system can be expressed as the function volume of the temperature as U times U to the V times temp. Enthalpy can be expressed as a function of pressure and temperature in relation with the defined with the thermodynamic property of specific heat. There are two versions of the property of the specific heat with the constant volume and the constant pressure of specific heat. The defined constant volume of specific heat and constant pressure of specific heat. The values of both of those properties vary greatly. Temperature of the most systems, small changes is temporary considered. However, constant specific heat may be assumed. The solids and incompressible liquid, the difference between the values of compressible constant pressure, specific heat, and constant volume of specific heat is negligible. Alright, 13.3 Material Systems. First and second law of thermodynamics describe the thermodynamic behavior of all substances. Further information is gained by studying how different substances react in thermodynamic interactions. Ideal gases. Any equation that states the relationship among the value of the property substance with a given state is called the equation of the state. This is observed with the relationship among the value of the property of gas of the equilibrium state, low pressure, and can be expressed in a very simple equation. Although the equation represents the idealized gas for the high temperature or low pressure for the area of the negligible, some gases such as helium, hydrogen, nitrogen behave like an ideal gas for most equilibrium states, while others such as steam behave like an ideal gas only at low pressures. Fair indication likelihood that a gas will behave like an ideal gas can be obtained looking at the molecular structure. Monoatomic, diatomic gases will almost always behave like ideal gases, but as complexity of the molecule increases, the values of the property of the gas will begin to deviate from the predicted ideal gas equation. Ideal gas equation is property of values RT. Pressure volt times the gas constant times temperature. Pressure volt volume of the system equals mass times the gas constant times the temperature. Pressure volt volume times the number of moles in gas system times the universal gas constant times the temperature. Well, universal gas constant is the name of the implies sum of the forces of all the gas constants are specific. Each gas can be found with the equation gas constant equal over the universal gas constant time over the mass or molecular weight for the ideal gas. Alright, then we got solutions and examples. Alright, simple compressible substances. The ideal gas assumption works on the simple substance with a high energy of the many substances that commonly encountered with as water behave in significantly different ways. Water from tap with the liquid, however, we place the water in a freezer, it becomes ice and solid. We will put the water in a pot, boil it, and becomes steam and gas. There are three principal phases within which any substance can exist in solid, liquid, gas. Explanation of the phases can be found when we examine the microstructure of substance, the lowest energy level substance. Molecularly arrange themselves in close packed or organized structures called lattice. Because the energy level is low, molecules are close together, intermolecular forces dominate with lattice structures. They're maintained because the molecules cannot be easily separated, displaced. The substance appears macroscopically as a solid. At energy, substance through the interaction with the environment changes the beginning of the display for the energy, and some of the molecules become great enough that the lattice structure will begin with the breakdown. A stage of the substance has to become some structure, but molecules easily display substance now appears macroscopically as liquid add even more energy within the substance. Eventually, the molecules will overcome the intermolar molecular forces. What happens with the substance will also lose signs of the structure. Molecules will be separated for far greater distances. At this point, molecules can move randomly with the substance appear with macroscopically or as a gas. Because these phases change behavior, we can expect the equation state that describe the equilibrium state. Most substances will greatly deal with the complicated with the ideal gas. Most part, vast quantity for experimental data used to predict equilibrium states of substances using either tabulated data, equilibrium correlations, graphical thermodynamics, surfaces. Equilibrium states are simple compressible substances that function as most two independent properties mathematically. Such a relationship can be represented in the surface of three-dimensional space, which acts as representative value of thermodynamic property. Representation has become the transition of thermodynamic pressure expressed in function specific volume of the temperature of the projection, such as the surface and planes, as shown in Figure 13.7. Equilibrium states of the more substances can be described in the diagram, as well as shown with the equilibrium state of the diagrams indicate the relationships among phases of the dome-shaped region of the PV diagram. Vapor dome states to fall on the left over the edge of the dome, completely liquid, but on the verge of the boiling. For states of the substance of the called the saturated liquid states of the fall on the right edge of the dome, and the completely gaseous, but are verge on condensing. For these states of the substances are called saturated vapor. The two regions are separated at a point at the top of the dome called the critical point under the dome. The substance exists for two differential homogeneous states. A portion of the substance is saturated liquid over the portion saturated vapor. Both portions exist at the same pressure and temperature. There is only one point of the thermodynamic surface at which the substance can exist at all three phases of the triple point. If lines constant temperatures are drawn with a PV diagram, an important feature of the compressible substance becomes apparent. The constant temperature lines of the vapor dome is exactly horizontal, indicating that as long as two phases of liquid and vapor are present, change of the state occur with the constant pressure will occur with the constant temperature, and change the amount of energy will serve with the more overall composition of substance, either closer to saturated liquid phase, closer to saturated vapor phase. The same type of the behavior is observed. The substance change and become between liquid and solid states. Thermodynamic tables, because of the graphical surface of the analyze of the current cumbersome of the equilibrium state of data. Many common substances have been compiled in tabular form. Most common of these tables are steam tables of the water. Examples are given at the end of the chapter. Usually two tables, one with saturated liquid, saturated vapor, equilibrium, shown on pages 399 and 400. One with superheated vapor, equilibrium, stage 401 of the water. These tables give the values, specific volume of the specific heat, initial energy, specific enthalpy, specific entropy, as function in the temperature and pressure of the saturated water. Table lists values as a function of either pressure and the temperature. Information available of these limited. These tables limited because the value of the few tables are given and what happened to information is needed about the state, not listed in the table for analyzing unusual sufficient linear interpole values of the property of the state that falls between the two states given in the tables. Vapor-liquid mixtures. A saturated vapor-liquid water table that provides data of the region of the thermodynamic surface of the vapor dome with the property data with the listed either as a function of the temperature, function of the pressure, sensitive to the pressure of the temperature, or relieve the saturated substance. Only one value is needed to determine the state of the saturated substance. Usually the value of the other property is given in references. Each of the dependent properties within the table, specific volume, specific internal energy, specific enthalpy, and entropy. This is a two-state saturated liquid state with no vapor present, denoted with the F subscript, saturated vapor state, and the liquid present denoted with the G subscript. The sum of the value of the G script is indicated with the difference between the value of the property with the saturated liquid and saturated vapor. A substance evaporates the saturated liquid as saturated vapor. To condense the saturated vapor, saturated liquid considered as a mixture of two homogeneous substances. Saturated liquid, saturated vapor, all the energy added with the removed, the system goes into changing with the phase of the liquid, analyzing it often necessary to determine the average value of the properties for the vapor-liquid mixture. Since the example of the properties listed in the table, additive extensive form is reported in mass-specific intensive form. The whole value of the substance can be calculated by using the mass-weighted average of the value of each of the table to give the rise of the parameter quality as defined as x equal to the mass of substance in vapor phase over the total mass of liquid and vapor combined. Or x is equal to m mass grams over the mass of the MFG and mg. Equation of the gas weighted average values of the mass specific properties or liquid vapor mixtures are as follows. Physiometrics. Often the environmental system analyzed with the substance makes up the system found to be in within air. Normally, air is assumed with a homogeneous mixture of the gases value of the thermodynamic property to be found in tabulated form. However, the value of the table to saturated standard for the composition gas for the composition of the air of the environment can change greatly over time, and the component most likely to affect the thermodynamic properties of the air is like an amount of water vapor air contains low humidity. Deal with a variation air is often considered the mixture of the two gases, dry air, with the thermodynamic property that could be found with the standard air table of the water vapor, the thermodynamic property of the given and the standard steam tables with the ideal with the gas mixture of the pressure of the dry air water vapor mixture is some of the partial pressure of these components are. Total pressure of the mixture is equal to the pressure of the partial pressure of the dry air plus the partial pressure of the water vapor. The composition of the air water vapor mixture can express the term of the mass ratio. Mole ratio of the two components, just as in ideal gas mixture. The mass ratio measure that is called the specific humidity that is given by specific humidity ratio of the mass of the water vapor over the mass of the dry air, or 0.622 over the pressure Y over pressure plus pressure V. The coefficient 0.622, the determinant of the ratio of the molar mass of water to dry air. Relative humidity is defined as relative humidity is equal to pressure volume of the saturation pressure volume of the temperature of the air water vapor mixture. 2-point temperature of the composition air water vapor mixture of the limited sum of the degree of the equilibrium states of the water. There is maximum amount of the water vapor the mixture can hold that any of the water added. To understand the idea of the consider the system of the consistent water only with a given temperature if the pressure of the water is below the saturation pressure of the temperature of the water exists as a vapor. If the pressure is greater than the saturation pressure of the water exists as a liquid. For any air-water vapor mixture, the pressure of the water vapor is partially with the pressure of the air as water is added to the end of the system. Partial pressure is increased until the equal in saturation pressure of the water given the temperature of the ends of the point with a mixture that cannot accept any more water into the vapor phase. To add additional water to the additive to the system is called the liquid phase. Saturation pressure of the water is a function of temperature. Therefore, any given pressure of the water system below the critical pressure of the air exists. The temperature for the which the pressure is saturation pressure. For an air-water vapor mixture of the air exists. The temperature for which partial pressure of the water vapor is equal to the saturation pressure of the water. The temperature is called the dew point temperature. The temperature of the mixture is reduced below the dew point. Some of the water vapor will begin to condense into the liquid condensation while it continues within the partial pressure of the water vapor is equal to the saturation pressure of the water at the lower temperature of which happens within the environment. Condensed water collects on solid particles into and becomes fog. Alright, wet bulb temperature. A common device used to experimentally determine the amount of the water vapor air with the humidity of the sling physiometer device consists of two glass tube thermometers mounted side by side with the handle attached to the top of the thermometer with the bulb of the thermometer converted with a fabric wick which saturated with water. This is a wet bulb thermometer. The other, the dry bulb thermometer, the device is operated by swinging its handle because there will be some energy transferred due to the evaporation water of the wick of the wet bulb thermometer. The two thermometers display the different temperatures. Differences used to determine the humidity of the air. The temperature read with the wet bulb thermometer is called the wet bulb temperature. For the air-water vapor mixture, the temperature read from the dry bulb temperature is the dry bulb temperature. Psychrometric chart. Psychrometric chart relates to the values, specific volume, specific enthalpy, relative humidity, wet, dry bulb temperatures, humidity ratio of the equilibrium states of mixture of the given pressure, given the values of any of the two properties again, determine values of all the others. Examples of psychrometric chart is found on page 403. 13.4 applications. Okay, might cut this chapter short. Alright, application. All the definition, all of the concept given above combine, analyze, predict the performance of real mechanical devices. Some of the examples of the devices are discussed below. Energy conversion division devices. Many of the energy conversion devices to which above the law of relationship can be applied. Each of these systems, steady state system, remaining rate of change of every property. Each of the location of the device will remain zero. The steady state of the assumption greatly simplifies the analysis based on those equations applied with the steady state system as follows: mass balances, energy balance, entropy balances. Nozzle diffusers diagram in figure 13.9 with the device changes the velocity of the pressure of the fluid system. Therefore, we will expect the kinetic energy of the true be significant. Analyzing off is simplified with the assumption of the effects due to the chain of the potential energy are negligible. The mass balance from energy balance and entropy balance Efficiency of the nozzle over the diffuser is given with a change of the kinetic actual of the device over the kinetic ideal of the device, where N is the nozzle diffuser efficiency and entropy is the isoentropic exit state. In perfect efficiency of the nozzle, no entropy will be produced. Value entropy will be at the same outlet and with the inlet with the reading nozzle. Without the sum of the entropy produced, the value of the entropy the exit state will be somewhat higher than that of perfect efficiency nozzle. Turbines, pump, and compressors. Turbine pumps and compressors shown in Figure 1310 are used to produce mechanical work from some of the internal energy of the substance with the mechanical work to increase the internal energy of the substance. Turbine energy is removed from the substance of the mechanical work interaction into the pump of the compressor. Energy transferred with the substance of the mechanical work interaction. Where the device is considered, the conversion of the energy is often assumed to take place adiabatically. That is, no heat interaction changes with the kinetic potential energy are often negligible from mass, from energy, and entropy balance of efficiency. Turbine pumps and compressors can be found using the following equations, and boilers and condensers evaporated the device used to change the phase for the substance of the boiler and evaporated diagram 1312 substance changed with the liquid to the vapor. The condenser vapor is changed into the liquid. These devices are used to take advantage of the relatively large amounts of energy transfer required to change phase of the common fluids. For the parts of boilers and condensers evaporated transfer their energy through heat interaction. Changes in potential kinetic energy are often negligible. Heat exchangers diagram Figure 1330. 13. The device allows energy to exchange between the two substances through the heat interaction. Analyzed simplified by assuming no other interactions take place, particularly there is no heat interaction between the heat exchanger and its environment. From mass balances, from H, hot steam to cold steam, for the energy balance, many cases change with the temperature of the heat exchanger small enough that the constant pressure of specific heat with a considered constant amount following equation used to place an equation from entropy and balance. Mixtures and separators. Mixtures and separators device combine separate material streams for the purpose of the discussion. Mixture and separator experience no work or heat interaction with it surrounding. No change of kinetic and potential energy is negligible. Thermodynamic cycle machine discussed earlier with the generalization of many cycle devices used in the industry. All the devices discussed here operate with thermodynamic cycle. There is a series of processes which end state with the last process equivalent to start state with the first process. Energy conversion device is often desirable to determine the figure of the merit of the thermodynamic cycle with the figure of the merit of the power producing thermodynamic cycle with thermal efficiency with the figures of the merit used with the refrigeration heat pump cycle coefficients of performance. Cannot cycle machine undergo the process without macro of the cycle of 4 steady state with the components, pistons, cylinders, steams, and induced type systems as shown in Figure 1315, 1350, 16. We'll stop at heat transfer. I'm getting kind of bored with this.